Hi, in this video I'm going to briefly introduce the RC circuit and the role of each component in the RC circuit. So what is an RC circuit? An RC circuit is a circuit with a resistor and a capacitor in series, and it'll look something like this. Here's my input voltage Vn of t. I have a resistor, resistance I, and then a capacitor in series with that resistor with capacitance C. So what's the role of each component in this circuit? Of course, Vn of t is the input voltage which comes from the power supply. The resistor, let's first talk about the capacitor. The role of the capacitor is to store energy electrostatically in between the two plates. And then the role of the resistor is to affect the rate at which the capacitor charges and discharges. So before we move on, I want to briefly review the functionality of a capacitor to make sure that we're on the same page. So, capacitors. Basic definition: it's a circuit component with two conducting surfaces and a dielectric in between. That's the basic definition. 2. The charge on the capacitor is related to the voltage across the capacitor through the relationship C equals Q over V, where C is the capacitance of the capacitor and its unit is farads. 3. The value of this capacitance C for any configuration is independent of the electric field in between the capacitor. So, if we assume parallel plate configuration, we have that the electric field in between the capacitor equals Q over epsilon times A. And since the electric field is uniform everywhere in between the two plates of the capacitor, the voltage across the capacitor is going to be E times D, where D is the distance between the two plates, which equals QD over epsilon A. And if I put this into this formula here, I get C equals Q over QD over epsilon A. And the Q's cancel out, and we're left with epsilon A over D, which, as you can see, is independent of the electric field in between the capacitor plates. 4. The charge on the capacitor cannot change instantaneously. Why? Because the current to the capacitor is related to the charge on the capacitor by I of t equals dq dt. So, if the charge on the capacitor were to change instantaneously, that would require an infinite current, which is not physically possible. Charge cannot change instantaneously. 5. Current does not actually flow through a capacitor, because if a DC voltage is applied to the plates of the capacitor, there is no conduction current flowing through the capacitor, assuming that the dielectric is an ideal insulator. So current does not flow through a capacitor. And the reason why a conduction current cannot flow through the capacitor or the dielectric in the capacitor is because there are simply no free charge carriers in the dielectric medium. Why? No free charge carriers. No free charge carriers in a perfect dielectric medium. So what happens is that positive charge flowing through the circuit, you'll have positive charge flowing through here. Positive charge will accumulate on the top plate of the capacitor, and this positive charge will create an electric field that will induce negative charge to come to the bottom plate of the capacitor until this positive charge and negative charge have the same magnitude. And now because negative charges went to the top of the plate of the capacitor, the positive charges that used to be on the plate of the capacitor continue through the circuit. So the rest of the positive charges continue through the circuit. So it looks as if that the positive charge, or the flow of current, went through the capacitor when it actually didn't. 6. In terms of energy storage, it's specifically these plus Q and minus Q charges on the top and bottom plate of the capacitor that allow the capacitor to store energy electrostatically in between its plates. Now, one might ask, assuming that the conducting material of the two plates has zero effective resistance and the dielectric is a perfect insulator, then no current can flow through dielectric, which we just talked about. Now, if that's the case, where does the energy go which is expended in order to charge up the capacitor? And the answer is that that energy gets stored in the electric field in between the plates of the capacitor. So the energy used to charge up the capacitor, is stored in the E field in the dielectric. And we can find this energy very easily by integrating the small work dW required to move a small charge dQ from the top plate to the bottom plate, and then integrating that over the total charge on the capacitor. And so if we do that, we find that the energy stored in the capacitor WE is the integral of dW, which turns out to be Q squared over 2C. Also, it's 1/2 CV squared. 7. This is just a manipulation of formulas. So we saw that C equals Q over V. Now, remember that I of t equals dQ dt, which equals d dt of CV, which equals, C is a constant, can go out the derivative, equals C dVt dt. And this is what we're going to use when we derive the differential equation that characterizes the RC circuit. So this concludes our introduction to the RC circuit, and in the next video we're going to derive the step response of the RC circuit.